Hi everyone. Recently I've been asked to talk a little bit about circular motion, horizontal circular motion around banked curves. Before I get into it, I want to introduce you to this little graphic that I've got on the screen right here. This is my attempt at drawing a cyclist. Now, you've got to imagine, you've got to use your imagination here, but this cyclist that we're looking at on the screen, is moving into the page at uniform motion, in uniform velocity. So as we think about that cyclist, we've got ourselves the tire that's in contact with the road. You can see here are the handlebars. This is the cyclist's head. So hopefully you can see that it's a cyclist. It's moving into the page away from us, the viewer. Our cyclist has got a whole bunch of forces acting on them. Now, they've got a drive force, which is moving them forward. They've got drag and resistance forces pulling them back. And these forces are cancelling each other out, and we're not going to concern ourselves with these forces throughout this video. There are also vertical forces acting on our cyclist. Now, the vertical forces acting on our cyclist, and I've drawn them in here, we've got a weight force and a normal force. In this scenario, where the cyclist is moving into the page in uniform motion, the weight force and the normal force are in opposite directions, and they're in equal magnitudes, and so they cancel each other out. They are balanced. In this situation, we say that there is no net force on the cyclist. And according to Newton's first law of motion, a body shall remain in uniform motion unless acted upon by a net external force. There is no net external force here. A couple of words about the normal force. The normal force is a special case of a reaction force. The reaction force is the ground acting on the cyclist, pushing the cyclist up. The normal force is a special case of the reaction force in which it's acting perpendicular to the surface of the ground. In this case, we have a normal force. Okay, now let's consider our cyclist is moving into the page, but we're going to have our cyclist now move in a circle to the left. As our cyclist moves in a circle to the left, still going into the page but moving in a circle to the left, we notice that the weight force doesn't change. It's the same magnitude, it's still straight down. But something has changed to our reaction force. We're no longer calling it a normal force because it's no longer at right angles to the surface. And equally, the other thing we notice about this reaction force is that the vector that's representing the reaction force in the diagram is now longer. The reaction force is now greater. This reaction force is applied to the cyclist from the road to the tires. It moves through their center of mass. Now, I've drawn the vector for this reaction force from the center of mass. That's what that black dot is there in our cyclist. We've got two forces that we're interested in here acting on the cyclist. There's the weight force pulling it down. There's the reaction force. And you can see here, even from the diagram, that these two forces are no longer balanced. The unbalanced sum of these two forces, we're going to call that the net force. And you can see in the diagram here it is yellow with dashed lines, the net force. This net force is horizontal to the left, and it's pointing towards the center of the circle that our cyclist is moving through. The net force is the sum of the weight and the reaction forces. The angle that our cyclist has had to lean at to move in this circular motion, we're going to call that angle for this time being theta. And if we go and take our reaction force and our weight force and turn them into a nice neat little triangle, summing them together, we can see the net force there, and we can see theta inside of that little triangle. A couple of words on the reaction force. The reaction force can be broken into horizontal and vertical components. Now, the vertical component is upwards, and it's equal in magnitude to the weight of our cyclist. Because the weight and the vertical component of the reaction are equal and opposite, they cancel each other out. And this tells us, therefore, that there is no acceleration of the cyclist up or down. So the vertical forces acting on our cyclist are balanced. The horizontal component of our reaction force acts parallel to the road surface, and it comes from the friction between the tires and the road. This horizontal component of our reaction force is what supplies the unbalanced net force. The unbalanced net force, the centripetal force acting on the cyclist, is coming from the horizontal component of the reaction. And this force is supplied by friction. Our cyclist must lean at an angle to move around this circle on our flat curve, because the reaction force, which is being acted onto the cyclist between the road and the tyre, has to pass through the centre of mass of the cyclist in order for the cyclist to maintain stability moving around the curve. If that reaction force doesn't act through the centre because the cyclist hasn't leaned, or maybe the cyclist has leaned too much, then we're going to see that the cyclist will not be able to stay upright as they move around the curve. They'll rotate either outwards or inwards. They'll fall over or fall off the bike. Mathematically, the net force, our unbalanced force on the cyclist, is due to the horizontal component of the reaction force. Now, our net force is a centripetal force, so we can say that the net force is equal to mv squared on r. When we look at the triangle of our reaction force and we look at the normal component and the parallel component, we can see that this lean theta has a relationship. Tan theta equals n on f parallel. Because of this relationship, we can say that the parallel component of our reaction force must equal n divided by tan theta. Since the weight force and the normal component of the reaction force are equal in magnitude, we can now say that mv squared on r is equal to weight divided by tan theta. This equivalence that you see on the screen now allows us to figure out the angle of the lean of our cyclist. So what if our cyclist is moving around a curve that is banked, a banked curve? Every banked curve, with whatever angle that it's banked at, will have a particular velocity or speed that the cyclist can move at, in which we don't require friction to keep our cyclist in their trajectory, in their path around the curve. In this scenario that you see on the screen here, we've got the cyclist moving into the page around the corner to the left, and you'll notice that we've once again labelled our reaction force a normal, because the angle of the cyclist on the page is at right angles or perpendicular to the surface of our banked curve. The normal force in this case does not balance the weight force. The net force of our cyclist is the unbalanced sum of these two forces. The normal force can be thought of as having a vertical component and a horizontal component. Because the normal force is acting from the tyres through the centre of mass of our cyclist, because the normal force is acting perpendicular to the surface, there is no part of the normal force which is up the bank or down the bank. And so friction does not play a part in the motion of this cyclist as they go around the curve. This is possible because the cyclist will be moving at exactly the right speed for this particular angle of banked curve. The curve is banked at an angle theta. Now, when we add our vectors of weight and our normal force, when we add these together graphically, we'll see that our unbalanced force is the normal force horizontal component, which is the same as the net force acting on the cyclist. In this particular triangle now, you'll see that the angle theta of our banked curve is the angle between the normal and the weight forces. Mathematically, the net force is equal to the horizontal component of the normal force. So mv squared on r is equal to weight tan theta. Where did weight tan theta come from? We look at our triangle there to the right and we see that tan theta is equal to the horizontal component, nx, over weight. So nx must equal weight tan theta. Tan theta equals mv squared on weight multiplied by the radius of our circle. We notice in the next line, because weight's equal to mg, the mass of our cyclist cancels out on the right-hand side of our equation, which means that our banked angle is equal to the inverse of tan for v squared on gr. What does this tell us? This tells us that this particular theta, this particular angle, will have a particular velocity, and the mass of our cyclist is irrelevant. Our cyclist will be safe to move around at this velocity around the curve regardless of their mass. So it could be a cyclist on a push bike, it could be a small car, it could be a truck. Provided our vehicle is moving at the appropriate velocity, they can go around that curve no matter what their mass is. Here's a question from the Exploring Physics problem set 4. A civil engineer has to design a road in which there is a curve with a radius of 300 meters. The road will have a maximum speed of 110 kilometers an hour, at which angle should the road bank on the curve so that no frictional force is needed by a vehicle traveling at the speed limit to move around it. Okay, so what are the important bits of our information here? The radius of the curve, 300 meters. Our velocity, 110 kilometers an hour, which is 30.6 meters per second, divided by 3.6. We know that our net force is equal to the horizontal component of our normal force. So mv squared on r equals weight tan theta. Tan theta equals mv squared over weight multiplied by radius. The masses cancel out, leaving us with theta is equal to tan to the neg1 of v squared over gr. 30.6 squared over 9.8 by 300 gives us an angle of bank equal to 17.62 degrees. And it should not matter if it's a cyclist, a motorcyclist, a car, or a truck. Okay, I hope that was useful.